So I wanted to take a few minutes here to finish up our session from the other day, from last week on Monday, when we talked about pharmacokinetics. The last measurable pharmacokinetic variable that we were looking at was for excretion. But looking more broadly, excretion is actually a component of a term called elimination, which comprises both excretion and metabolism. Elimination proceeds either exponentially and proportionally to the plasma concentration per unit time. This is termed first-order elimination. Or it proceeds constantly in a linear fashion, and this is termed zero-order elimination. The slope of the first-order curve is actually described by a variable known as K, sometimes seen as Ke or Kel. Ke describes the fraction of drug eliminated per unit time, or the rate at which the plasma concentration will decrease during the elimination phase. So it turns out that Ke is really important for determining the T1/2 of a drug, the time until a drug is completely cleared from the system, and the time to reach steady state, which is a key parameter that's involved in determining infusion rates for IV infusions. To bring this to life, let's consider an example. If 10% of drug X were eliminated per hour, then the Ke would equal 0.10 per hour. This means that 10% of the drug will be eliminated per hour, whether the starting dose is high or low. It's a constant fraction of the drug that's eliminated per unit time. As noted, Ke can be used to calculate T1/2. We'll see that in the next slide. And in fact, T1/2 and Ke are inversely proportional. So based on this relationship between Ke and T1/2, we can make a couple statements here about drugs and how they behave. The first is that it takes about 4 to 5 T1/2s for a drug to be eliminated by about 95 to 97%. The second is that it takes about 4 to 5 T1/2s for a drug to reach steady state level. We'll talk about this idea of steady state more on Monday when we go through the formulas. Before we move on, there's one last thing we can say when comparing first-order and zero-order elimination. Increasing the dose of a drug eliminated by first-order kinetics does not alter the T1/2. However, increasing the dose of drugs eliminated by zero-order kinetics does alter the T1/2 because the elimination is constant and can be saturated. So let's move on to look at how we can actually quantify and calculate elimination. We do this by measuring clearance, that is the volume of blood that's cleared of drug per unit time. And you can see that clearance is equal to the rate of elimination over the concentration of drug. This is only one part of a broader idea, however. Total clearance is equal to clearance for each of the individual organs that a drug would come in contact with. So, getting back to the idea of T1/2, we see K again, our elimination rate constant, and it's inversely related to T1/2. The 0.693 that's shown here is the natural log of 2 being derived from 100% divided by 50%. So literally the definition of half. Using T1/2 and some other derivation that I won't show here, we can actually get a formula for clearance where clearance is equal to the volume of distribution times the elimination rate constant. We'll put this into action on Monday in those cases. Finally, I leave you with a figure that shows the intersection between clearance and metabolism. So we talked about two different types of metabolic pathways, phase 1 and phase 2, and how really the goal of these metabolic pathways is to make a drug more water soluble and enhance its excretion, thus its elimination. And we can see that in action right here. We have a parent drug here. This drug has been acted upon by phase 1 enzymes. And then phase 2 enzymes that have added a glucuronide here. And what we see is if we look at this axis, we can see as we've made these modifications, both from phase 1 and phase 2, it increases the degree to which this drug is going to be cleared. So it increases its water solubility. And to prove that, you can look at this axis, the x-axis down here on the bottom, log D. And this might look familiar if you remember when we talked about the oil-water partition coefficient. So as the drug moves in this direction, more oil soluble. As it moves in this direction, more soluble in water. That's all I have for you guys. I look forward to working on these cases with you next week. And please let me know if you have any questions. Thanks very much.